Hello, and welcome. It's good to have you here, wherever you are, whatever time it is where the night has found you. Tonight, we're going to drift toward a place in the solar system where silence takes on shape, where gravity has drawn billions of frozen fragments into patterns so delicate and so vast that they seem almost impossible. We're traveling to Saturn, the ringed giant, a world that moves through space with a kind of unhurried grace, carrying around itself a structure more intricate than anything human hands have ever built. You can let your shoulders settle, if you'd like. There's no need to hold anything tightly right now. Perhaps you've had a long day. Perhaps your mind is still turning over the small concerns that gather in the hours before sleep. That's all right. You don't need to set them down completely. Just let them rest beside you for a while, as we turn our attention outward, beyond the sky, beyond the familiar glow of Earth's atmosphere, towards something vast and quiet and endlessly patient. If these journeys bring you comfort, you're welcome to return anytime. There will always be more to explore, more gentle facts waiting in the dark. So let's begin, slowly, with the simplest truth. Saturn exists. It moves through the cold and the silence, far from the sun, wrapped in its own stillness. And tonight, we'll let that stillness find us too. Saturn is the sixth planet from the sun, and it sits at a distance that seems almost unimaginable. About 1.4 billion kilometers separated from the star that warms our days. Light itself, traveling faster than anything we know, takes nearly an hour and 20 minutes to cross that gulf. If you were to look at Saturn through a telescope right now, you would not be seeing it as it is in this moment. You would be seeing it as it was more than an hour ago, a vision carried across space at the speed of light, patient and unchanging. This distance gives Saturn a certain kind of peace. The sun, from Saturn's perspective, is smaller, dimmer, a pale disk that offers only a fraction of the warmth and light we feel here on Earth. In fact, sunlight at Saturn is about 1% as strong as it is on our world. The planet exists in a kind of perpetual twilight, a soft, diffuse glow that never brightens into the harsh clarity of a summer afternoon. It is always dusk there, always gentle, always cool. And yet, despite this remoteness, despite the cold and the distance, Saturn is not a small world. It is enormous. If you could somehow gather 163 Earths and press them together, you would approach the volume of Saturn. It is the second largest planet in our solar system, smaller only than Jupiter, and it carries its size with a kind of quiet dignity. There is nothing aggressive about Saturn. It does not roar or flash or demand attention. It simply exists, vast and serene, turning slowly in the dark. The planet completes one orbit around the sun every 29.5 Earth years. Imagine that. A single year on Saturn lasts nearly 3 decades. If you were born at the beginning of a Saturnian year, you would be approaching middle age by the time that year ended. Seasons there unfold with a slowness that feels almost geological. Summer arrives and lingers, not for months, but for years. Winter stretches across nearly a decade. The planet does not rush. It has no need to. And as it moves through this long, slow orbit, Saturn rotates on its axis with surprising speed. A single day on Saturn lasts only about 10.5 hours. The planet spins so quickly that it bulges at its equator, flattens slightly at the poles by the force of its own rotation. It is not a perfect sphere. It is softer than that, rounder at the middle, as if the planet itself is relaxed, unhurried, content to let its shape reflect the gentle physics of spin and gravity. This rapid rotation gives Saturn another gift, a powerful magnetic field. Deep within the planet, beneath layers of cloud and gas, beneath the strange, fluid hydrogen that makes up most of its interior, electric currents flow. These currents generate a magnetic field that extends far out into space, creating an invisible bubble around the planet, a magnetosphere that shields it from the solar wind, from the charged particles that stream constantly outward from the sun. This bubble is vast. It stretches for millions of kilometers, and within it, Saturn's moons move in relative safety, protected by the planet's quiet strength. But we are not here only for Saturn itself. We are here for the rings. The rings of Saturn are perhaps the most beautiful structure in the solar system. They have captivated human imagination for centuries, ever since Galileo first turned his primitive telescope toward the planet in 1610 and saw something strange, something he could not quite understand. He thought, at first, that Saturn had ears or handles, bulges on either side that made no sense. His telescope was not strong enough to resolve the rings clearly. It would take decades and better instruments before astronomers understood what they were seeing: a flat, wide disk of material, impossibly thin, impossibly delicate, encircling the planet like a halo. The rings are made of ice, mostly ice, billions upon billions of individual particles, each one following its own orbit around Saturn, each one a tiny moon in its own right. Some of these particles are as small as grains of sand. Others are as large as houses or mountains. They tumble slowly through space, colliding gently with one another, reflecting sunlight, glittering in the pale glow that reaches them from the distant sun. And they are thin, astonishingly thin. The rings of Saturn stretch across a distance of more than 280,000 kilometers from edge to edge, and yet, in most places, they are only about 10 meters thick. Imagine a sheet of paper scaled up to the size of a city. That is the proportion we're talking about. The rings are so flat, so delicate, that if you could somehow stand on the edge and look across, you would see a structure that seems almost two-dimensional, a line drawn across the void. But despite their thinness, the rings are not fragile. They have existed for a long time, perhaps hundreds of millions of years, perhaps longer. They are held in place by gravity, by the pull of Saturn itself, and by the subtle gravitational influences of the planet's many moons. The rings do not drift or scatter. They remain patient and persistent, a testament to the quiet power of physics. There are several main rings, each one separated from the others by gaps and divisions. The names are simple, alphabetical, assigned in the order they were discovered rather than the order they appear. The A ring is the outermost of the bright, main rings. The B ring is the broadest and the brightest, a thick band of ice that reflects more light than any other part of the system. The C ring is dimmer, more translucent, a ghostly presence closer to the planet. And beyond these, there are others: the D ring, the E ring, the F ring, each one with its own character, its own story. The gaps between the rings are not empty. They are regions where the gravitational influence of Saturn's moons has swept particles away, creating spaces, clearings in the ice. The most famous of these is the Cassini division, a wide gap between the A and B rings, named after the astronomer Giovanni Domenico Cassini, who first observed it in 1675. The Cassini division is not completely empty, but it is noticeably darker, less dense, a quiet boundary between two of the most prominent rings. And within the rings themselves, there are waves, not waves of water, but waves of density, ripples that move through the particles like sound through air. These waves are caused by the gravitational pull of Saturn's moons, by resonances, places where the orbital period of a ring particle matches some simple fraction of a moon's orbital period. When this happens, the moon's gravity tugs on the particles again and again in the same way, at the same point in their orbit, and over time, this repeated tugging creates patterns, spirals, waves that propagate through the ring like echoes. Some of these waves are called density waves. They are places where particles bunch together, where the ring becomes slightly thicker, slightly brighter. Other waves are called bending waves, places where the ring itself warps up and down, tilting slightly out of its usual plane. These waves are subtle, often invisible to the naked eye, but spacecraft have measured them, mapped them, traced their shapes across thousands of kilometers. They are evidence of a hidden order, a mathematical beauty that emerges from the simple laws of gravity. The rings are not uniform. They are not smooth. Up close, they reveal an astonishing level of detail, a texture that seems almost organic. There are narrow ringlets, tightly packed bands of particles that wind through the broader rings like threads. There are gaps and clearings, some only a few kilometers wide. There are regions where the particles clump together into temporary aggregations, proto-moonlets that form and dissolve and form again, never quite coalescing into something permanent. And there are shepherding moons, small satellites that orbit just inside or just outside certain rings, their gravity acting to confine the ring particles, to keep them from spreading out. The F ring, for example, is kept in place by two small moons, Prometheus and Pandora, which orbit on either side of it. These moons are not large, only 100 kilometers or so across, but their gravitational influence is enough to shape the ring, to create kinks and braids and clumps in the ice. The F ring is one of the most dynamic parts of the ring system, constantly changing, constantly reshaping itself in response to these gravitational shepherds. The rings are bright because they are made of ice, and ice is one of the best reflectors of sunlight in the solar system. The particles are mostly water ice, frozen solid in the cold of space. Their surface is clean and reflective. This is why Saturn's rings are so visible, even from Earth, even across the vast distance that separates us. They catch the dim sunlight and throw it back toward us, a pale gleam in the darkness. But the ice is not pure. Mixed in with the water ice are traces of other materials, rocky dust, organic molecules, perhaps even tiny amounts of methane and ammonia. These impurities give the rings a slight color, a faint warmth, though to the human eye they would still appear mostly white or pale gray. Some regions of the rings are slightly redder than others, stained by the slow accumulation of dust and debris over millions of years. The origin of the rings is still a matter of scientific debate. There are two main theories. The first suggests that the rings are ancient, formed at the same time as Saturn itself, more than 4 billion years ago, from the same cloud of gas and dust that collapsed to create the planet. According to this idea, the rings are primordial, a remnant of the solar system's birth, preserved in the cold and the dark. The second theory suggests that the rings are much younger, perhaps only a few 100 million years old. According to this idea, the rings formed when a moon or a comet wandered too close to Saturn and was torn apart by tidal forces, the same forces that create ocean tides on Earth. When an object comes too close to a planet, the gravitational pull on the near side is stronger than the pull on the far side, and if the object is not held together strongly enough, it can be stretched and broken. The boundary where this happens is called the Roche limit, and it lies just outside Saturn's cloud tops. Anything that crosses the Roche limit and is not held together by its own internal strength will be pulled apart, its fragments spreading out into a ring. Recent evidence from the Cassini spacecraft, which orbited Saturn for 13 years, suggests that the rings may indeed be relatively young. The ice particles are very clean, very bright, which suggests they have not been exposed to the slow rain of cosmic dust for billions of years. If the rings were ancient, they would likely be darker, dirtier, more contaminated. But they are not. They gleam. This suggests they may have formed more recently, perhaps from the breakup of a moon within the last few 100 million years. But whether they are ancient or young, the rings are not eternal. They are slowly disappearing. The ice particles are constantly colliding with one another, and these collisions generate electric charges. Charged particles interact with Saturn's magnetic field, and this interaction causes them to spiral slowly inward, falling like rain onto the planet's upper atmosphere. Scientists call this ring rain, and it is happening all the time, silently, invisibly. Every second, thousands of kilograms of water ice fall from the rings into Saturn's clouds. At this rate, the rings may vanish entirely within a few 100 million years, a blink of an eye in cosmic terms. So if the rings are young, and if they are disappearing, then we are living in a special time. We are alive at a moment when Saturn has rings, when this delicate structure happens to exist. A billion years ago, Saturn may have been ringless. A billion years from now, it may be ringless again. We are witnessing something temporary, something rare, something that will not last forever. This thought carries a certain kind of comfort. The rings remind us that beauty does not need to be eternal to be meaningful. They exist now, in this moment, and that is enough. Saturn itself is a gas giant, which means it has no solid surface. If you could somehow descend through its atmosphere, you would pass through layers of cloud, layers of gas, the pressure and temperature rising steadily as you fell. Eventually, the gas would become so dense, so compressed, that it would behave more like a liquid than a gas. Deeper still, the hydrogen that makes up most of the planet would transform into a strange state of matter called metallic hydrogen, a form of hydrogen that conducts electricity like a metal. This is where Saturn's magnetic field is generated, in the slow, convective currents of metallic hydrogen deep within the planet. At the very center, there may be a core, a solid mass of rock and ice, perhaps 10 to 20 times the mass of Earth, but no one knows for sure. The core is hidden beneath tens of thousands of kilometers of gas and liquid, unreachable, unknowable, a mystery at the heart of the giant. The atmosphere of Saturn is mostly hydrogen and helium, the two lightest elements, the two most common elements in the universe. But there are traces of other substances as well: methane, ammonia, water vapor, and more complex organic molecules. These trace gases give the planet its color, a pale gold, a soft buttery hue that seems warm despite the cold. The clouds are arranged in bands, parallel to the equator, driven by the planet's rapid rotation. These bands are regions of rising and falling gas, convection cells on a planetary scale, and they create winds, powerful jet streams that race around the planet at speeds of up to 1,800 kilometers per hour. But unlike Jupiter, where the bands and storms are sharp and vivid, Saturn's atmosphere is softer, hazier, more muted. A layer of high-altitude haze obscures the deeper clouds, giving the planet a smooth, almost featureless appearance. There are storms, yes, and occasionally a great white spot will erupt, a massive convective outbreak that can grow to the size of Earth. But most of the time, Saturn appears calm, serene, a world of gentle gradients and soft transitions. The temperature at the cloud tops is about minus 140 degrees Celsius. It is cold, far colder than anywhere on Earth, but not as cold as the outer reaches of the solar system. And deep within the planet, the temperature rises. At the core, it may reach 10,000 degrees Celsius or more. Hotter than the surface of the sun, Saturn radiates more heat than it receives from the sun, a slow, steady glow powered by the planet's gradual contraction, by the slow settling of helium through the hydrogen layers. This internal heat drives the weather, the winds, the storms. Saturn is not a dead world. It is active, dynamic, alive in its own way. The planet is tilted on its axis, just like Earth. The tilt is about 27 degrees, which means Saturn experiences seasons. But because a year on Saturn lasts nearly 30 Earth years, each season lasts more than 7 years. Right now, as I speak, Saturn is moving through its northern summer, and the rings are tilted toward the sun, illuminated from above. In a few years, the planet will reach its equinox, and the rings will be edge-on to the sun, casting long shadows across the cloud tops. Then, slowly, the southern hemisphere will tilt toward the sun, and a new season will begin. These seasonal changes affect the entire Saturnian system. The temperature shifts, the atmospheric circulation changes, and even the rings respond. During equinox, when the sun shines edge-on through the rings, shadows and light reveal structures that are invisible at other times. Vertical features, tiny moons embedded in the rings, even the slight warping of the ring plane, all become visible in the slanting light. Saturn has more than 80 moons, a family of worlds that orbit the planet at various distances, each one unique. Some are large, with their own atmospheres and geologies. Others are small, irregular chunks of rock and ice, captured asteroids or fragments of larger bodies. The largest moon, Titan, is bigger than the planet Mercury. It has a thick atmosphere, rivers and lakes of liquid methane, and a complex organic chemistry that may resemble the early Earth. Titan is a world unto itself, a place of mist and rain and distant, orange skies. But there are other moons, smaller and quieter, that play a crucial role in shaping the rings. Mimas, for example, is a medium-sized moon that orbits just outside the rings. Its gravity creates the Cassini division, sweeping particles out of that region through a resonance. Enceladus, another small moon, orbits farther out, and it is one of the most remarkable places in the solar system. Enceladus has geysers, plumes of water vapor and ice that erupt from cracks in its south polar region and spray out into space. Some of this material falls back onto the moon, but much of it escapes, forming a faint, diffuse ring called the E-ring, a vast torus of tiny ice particles that encircle Saturn. The moons and the rings are connected, part of a single, integrated system. The moons shape the rings, and the rings, in turn, may be the source of some of the moons. Small moonlets, embedded within the rings, accrete material over time, growing slowly, perhaps eventually migrating outward to become independent satellites. The system is dynamic, constantly evolving, constantly reshaping itself. And yet, for all this activity, there is a profound stillness to Saturn. The planet does not shout. It does not demand. It simply exists, turning slowly in the dark, its rings catching the light, its moons moving in silent procession. There is something deeply calming about this, something that invites contemplation. When we look at Saturn, we are looking at a world governed by simple laws: gravity, motion, thermodynamics. And yet, from these simple laws, extraordinary complexity emerges. The rings are not designed. They are not planned. They are the natural consequence of ice and gravity and time, and they are more beautiful than anything we could have imagined. This is one of the quiet miracles of the universe. Beauty does not require intention. It arises spontaneously from the mathematics of nature. The rings themselves are not solid, though from a distance they might appear to be. They are made of countless individual pieces, each one orbiting Saturn independently, following the same laws that govern moons and planets. Some pieces are as small as grains of sand. Others are as large as mountains. They do not touch each other often, though occasionally they do collide, gently, in the silence of space. When they do, they might shatter into smaller pieces, or they might simply bounce away, continuing their endless journey around the planet. The rings are not crowded. There is space between each particle, sometimes vast space, though from far away they seem like a single unbroken surface. The rings are divided into sections, each one given a letter. The letters do not follow alphabetical order, because they were named in the order they were discovered, not in the order they appear. The brightest ring is called the B ring. It is the widest and most opaque, reflecting sunlight with a brilliance that can be seen even through small telescopes from Earth. Next to it, closer to the planet, is the C ring, which is much darker and more transparent. Beyond the B ring, farther from Saturn, lies the A ring, another bright band separated from the B ring by a gap. This gap is called the Cassini division, named after the astronomer who first noticed it in the 17th century. It is not truly empty, but contains far fewer particles than the rings on either side, making it appear as a dark line when viewed from a distance. The Cassini division is nearly 5,000 kilometers wide. That is wider than the entire continent of Europe. And yet, within that apparent emptiness, there are still particles, still ice, still faint ringlets that circle the planet in near silence. The division exists because of gravitational resonance. A moon called Mimas orbits farther out, and its gravity tugs on particles in that region, clearing them away over millions of years. It is a slow process, patient and inevitable, like water smoothing a stone. Beyond the A ring, there are fainter rings. The F ring is narrow and twisted, shaped by the gravity of two small moons that orbit on either side of it, shepherding its particles into place. The F ring changes shape over time. Sometimes it appears braided, with strands that weave around each other. Sometimes it develops bright clumps that move along its length. These clumps may be caused by collisions or by the gravitational pull of tiny moonlets embedded within the ring itself. The F ring is dynamic, restless in its own quiet way, never quite settling into a single form. Farther still, there is the E ring, which is enormous. It extends from the orbit of Mimas all the way out to the orbit of Rhea, a distance of hundreds of thousands of kilometers. The E ring is so diffuse that it is nearly invisible. Its particles are incredibly small, mostly microscopic grains of ice. They are supplied by Enceladus, a small moon that orbits within the ring. Enceladus has geysers at its south pole, jets of water vapor, and ice that spray into space. These particles are caught by Saturn's gravity and spread out into a vast, thin halo. The E ring is not ancient like the main rings. It is constantly being replenished, a living ring fed by the moon within it. There is also the G ring, faint and narrow, and beyond it the enormous Phoebe ring, discovered only in 2009. The Phoebe ring is so large that it could contain 1 billion Earths within its volume. It is tilted at an angle to the other rings, and it is made of dark particles that come from the moon Phoebe, which orbits far from Saturn in a retrograde direction, moving opposite to the planet's rotation. The Phoebe ring is invisible to ordinary telescopes. It was found by detecting its faint infrared glow, the heat of its particles warmed by the distant sun. Each ring has its own character, its own structure, its own story. And within the rings, there are gaps. Some are wide, like the Cassini division. Others are narrow, only a few kilometers across. These gaps are often caused by moons, either large ones far away or small ones embedded within the rings themselves. The moons carve out space with their gravity, sweeping particles aside, creating empty lanes in the flow of ice. One of these gaps is called the Encke Gap, a narrow division within the A ring. It is only about 300 kilometers wide, but within it orbits a tiny moon called Pan. Pan is only about 30 kilometers across, shaped somewhat like a walnut or a flying saucer, with a ridge around its equator. That ridge was formed by ring particles that fell onto the moon over time, building up around its middle. Pan keeps the Encke Gap clear, acting as a shepherd, though some particles do drift into the gap and create faint ringlets on either side of the moon's path. There is another moon, even smaller, called Daphnis. It orbits within a gap in the outer part of the A ring, a gap called the Keeler Gap. Daphnis is only about 8 kilometers across, barely large enough to be called a moon. But its gravity is enough to create waves in the edges of the gap, ripples that rise and fall as the moon passes by. These waves are vertical, standing up out of the plane of the rings like frozen ocean swells. They are a beautiful reminder that gravity is not just a force that pulls things down. It can also push, twist, and shape. The particles in the rings are not all the same. Some are pure ice, bright and reflective. Others are mixed with dust, giving them a darker, reddish color. The dust may come from micrometeorites, tiny specks of rock that strike the rings at high speed, vaporizing on impact and leaving behind a fine coating. Over time, this dust accumulates, darkening the ice. But collisions between particles can also chip away the dust, exposing fresh ice underneath, which is why some parts of the rings remain so bright. The rings are not flat, though they appear to be. They have texture. In some places, particles clump together, forming temporary clusters. In other places, the rings develop waves, not just at the edges of gaps but throughout their structure. These waves can be caused by the gravity of Saturn's moons, or by the gravity of the planet itself, which is not perfectly uniform. Saturn bulges at its equator because of its rapid rotation, and this bulge creates a gravitational field that is slightly stronger in some directions than others. This uneven pull can set particles in motion, creating patterns that ripple through the rings like wind across a field of wheat. Some of these patterns are called density waves. They are regions where particles bunch together, creating brighter bands that spiral outward from the planet. Density waves are caused by gravitational resonances, places where the orbital period of a ring particle is a simple fraction of the orbital period of a moon. For example, if a particle orbits Saturn 3 times for every 2 orbits of a moon, the moon's gravity will tug on the particle in the same place every few orbits, gradually amplifying the effect. Over time, this creates a wave that propagates through the ring, a pattern of compression and rarefaction that can stretch for thousands of kilometers. There are also bending waves, which move vertically rather than horizontally. These waves cause the rings to ripple up and down, like a flag waving in a breeze. Bending waves are also caused by resonances, but they affect the tilt of the particles' orbits rather than their distance from the planet. The result is a structure that is not entirely flat, but has a gentle, undulating shape, though the amplitude of these waves is usually only a few meters. The rings are full of such details, patterns within patterns, structures that reveal the hidden influence of gravity. They are a laboratory for understanding orbital mechanics, a place where the laws of motion are written in ice and shadow. Scientists study the rings not just to learn about Saturn, but to understand how planets form, how disks of material evolve, and how gravity shapes the universe on every scale. The rings are also very thin. Though they stretch across hundreds of thousands of kilometers, their vertical thickness is often only 10 to 30 meters. If you could shrink the rings down to the size of a piece of paper, they would be thousands of times thinner than that paper. This thinness is maintained by collisions. When particles bump into each other, they exchange energy and momentum. Over time, this process damps out any vertical motion, flattening the rings into a single plane. It is a gradual process, but it is constant, and it keeps the rings as thin as a whisper. And yet, despite their thinness, the rings contain an enormous amount of material. The B ring alone is estimated to contain enough ice to fill a moon the size of Mimas. All of the rings together may contain the equivalent of a small moon, spread out into a vast, glittering disk. This raises a question. Where did all this material come from? One possibility is that the rings are the remains of a moon that was destroyed. Perhaps a small moon wandered too close to Saturn and was torn apart by tidal forces, the same forces that create the Roche limit. Or perhaps a moon was struck by a comet or asteroid, shattered into countless pieces that spread out into a ring. Another possibility is that the rings are made of material that never formed into a moon in the first place, leftover debris from the early solar system that has orbited Saturn ever since. Scientists are still working to answer this question, studying the composition and structure of the rings for clues. Recent observations suggest that the rings may be younger than Saturn itself. They may have formed only a few 100 million years ago, which is recent in geological terms. This idea comes from measurements of how much dust and meteoritic material has accumulated in the rings. If the rings were as old as Saturn, they should be much darker and dirtier than they are. The fact that they are still so bright suggests that they are relatively young, or that they are constantly being renewed by some process. This is still a matter of debate, and future missions may provide more answers. The rings also interact with Saturn's magnetosphere, the region of space dominated by the planet's magnetic field. Saturn's magnetic field is strong, about 600 times stronger than Earth's, and it extends far into space, forming a protective bubble around the planet. Charged particles from the solar wind are trapped in this bubble, spiraling along magnetic field lines and creating radiation belts similar to Earth's Van Allen belts. The rings sit within this magnetosphere, and they absorb some of the charged particles, creating a shadow in the radiation belts. This shadow can be detected by spacecraft, a dark gap in the glow of high-energy particles. The rings also produce their own faint atmosphere. When charged particles strike the ice in the rings, they can knock water molecules loose, creating a thin cloud of water vapor and oxygen. This atmosphere is incredibly tenuous, far thinner than the best vacuum we can create on Earth, but it is there a ghostly presence that surrounds the rings. Some of this material escapes and falls into Saturn's atmosphere, contributing to the planet's chemistry. Saturn's magnetic field also creates auroras, just like Earth's. These are glowing curtains of light that appear near the planet's poles, caused by charged particles colliding with the upper atmosphere. Saturn's auroras are not visible in ordinary light, but they shine brightly in ultraviolet and infrared wavelengths. They are vast, much larger than Earth's auroras, and they are influenced by the solar wind, by the planet's rotation, and by the moons, especially Enceladus, which contributes water vapor to the magnetosphere. The planet itself rotates quickly, as we have already noted, but measuring that rotation precisely has been surprisingly difficult. Unlike Earth, Saturn has no solid surface that can be tracked. Its clouds move at different speeds depending on latitude and altitude, so they cannot be used as a reference. Scientists have tried to measure the rotation by observing the period of Saturn's magnetic field, but the magnetic field does not seem to be perfectly aligned with the planet's rotation axis, and it may even vary slightly over time. The best current estimate is that Saturn's rotation period is about 10 hours and 33 minutes, but this number may still be refined. This rapid rotation has shaped the planet in profound ways. It has created this strong equatorial bulge, which affects the orbits of the rings and moons. It has also created powerful winds in the atmosphere, winds that blow in alternating directions at different latitudes, forming bands of clouds that circle the planet. These winds are driven by heat from the planet's interior, which rises through the atmosphere and creates convection currents. The winds are incredibly fast, reaching speeds of up to 1,800 kilometers per hour near the equator, faster than the strongest hurricanes on Earth. Saturn's atmosphere is mostly hydrogen and helium, the same elements that make up the Sun, but there are also traces of other substances: methane, ammonia, water vapor, and complex hydrocarbons. These trace gases create the colors we see in the clouds. Ammonia ice forms white clouds in the upper atmosphere. Deeper down, where the pressure is higher and the temperature warmer, there are clouds of ammonium hydrosulfide, which have a brownish color. Deeper still, there are clouds of water ice. These layers of clouds create the banded appearance of the planet, though the bands are much more subtle on Saturn than on Jupiter. Saturn's atmosphere is calmer than Jupiter's in some ways. It has fewer large storms, and its bands are less distinct, but it is not entirely peaceful. Occasionally, massive storms erupt in the atmosphere, storms that can grow to encircle the entire planet. These storms are rare, appearing roughly once every Saturnian year, which is about 30 Earth years. They are called great white spots because they appear as bright, white regions against the planet's pale clouds. The most recent great white spot appeared in 2010, a massive storm that began as a small bright spot and grew over the course of several months, eventually wrapping around the entire planet at its latitude. The storm generated lightning, powerful winds, and enormous plumes of material that rose high into the atmosphere. These storms are thought to be caused by convection, the same process that drives weather on Earth. Heat from the planet's interior builds up in the lower atmosphere, creating instability. Eventually, this instability is released in a sudden, violent upwelling of gas, which breaks through the upper cloud layers and creates a storm. The storms eventually dissipate as the energy is released, but they can last for months, churning the atmosphere and creating features that are visible even from Earth. Saturn also has a faint system of polar hexagons, though the most famous is the one at the North Pole. This hexagon is a jet stream, a river of wind that flows in a perfect six-sided shape around the pole. Each side of the hexagon is about 13,000 kilometers long, wider than the diameter of Earth. The hexagon rotates with the planet, completing one rotation every 10.5 hours. It is a stable feature, having been observed for decades, though its color and contrast can change with the seasons. The hexagon is thought to be created by the interaction of different wind speeds at different latitudes. Computer simulations have shown that rotating fluids can spontaneously form polygonal shapes under the right conditions, and Saturn's atmosphere seems to provide those conditions. The hexagon is not unique to Saturn. Similar shapes have been created in laboratory experiments, but it is by far the largest and most stable example we know of. At the center of the hexagon, directly over the North Pole, there is a massive vortex, a swirling storm with an eye like a hurricane. This vortex is thought to be a permanent feature, driven by the planet's rotation and the flow of heat from the interior. The South Pole has a similar vortex, but no hexagon. Instead, it has a more circular jet stream, though the reasons for this difference are not entirely understood. The South Pole vortex also has an eye, and it is surrounded by towering clouds that reach high into the atmosphere. The vortex is warm compared to the surrounding atmosphere, suggesting the heat is rising from deep within the planet. Saturn's atmosphere is also home to smaller features, though they are often difficult to see because of the planet's pale color and the haze that covers the upper atmosphere. There are small storms, eddies, and waves that move through the clouds, driven by the winds and the convection below. There are also features called string of pearls, chains of small storms that appear at certain latitudes, possibly related to the same processes that create the great white spots. The planet's interior is still largely a mystery. We cannot see inside Saturn, but we can infer its structure from its mass, its size, and the way it responds to gravity. The outermost layer is the atmosphere, which gradually becomes denser and hotter as you descend. There is no clear boundary between the atmosphere and the interior. The gas simply becomes thicker and thicker until it transitions into a liquid. This liquid hydrogen layer is enormous, making up most of the planet's volume. The pressure in this layer is immense, millions of times the pressure at Earth's surface, and the temperature rises to thousands of degrees. Deeper still, the pressure becomes so great that hydrogen changes its properties. It becomes metallic, conducting electricity like a metal. This metallic hydrogen layer is thought to be where Saturn's magnetic field is generated, created by the motion of electrically conducting fluid in the planet's interior. The exact mechanism is still not fully understood, but it is similar to the process that generates Earth's magnetic field, though on a much larger scale. At the very center of Saturn, there may be a core made of rock and ice, heavier elements that sank to the center when the planet formed. This core is thought to be about 10 to 20 times the mass of Earth, though its exact size and composition are uncertain. The core is incredibly hot, perhaps as hot as the surface of the Sun, and it is under immense pressure, compressed by the weight of the entire planet above it. Saturn radiates more heat than it receives from the Sun. This is because the planet is still slowly contracting, a process left over from its formation. When Saturn formed, it was much larger and hotter than it is now. Over billions of years, it has been cooling and shrinking, and as it does, gravitational energy is converted into heat. This heat flows outward, warming the atmosphere and driving the weather. It is a slow process, but it is still happening, and it will continue for billions of years to come. The planet's moons are as varied as the rings are intricate. Saturn has at least 83 known moons, and there are likely many more small ones waiting to be discovered. These moons range in size from tiny, irregular chunks of rock and ice only a few kilometers across, to Titan, which is larger than the planet Mercury. Each moon has its own story, its own geology, its own mysteries. Titan is the most famous of Saturn's moons, and for good reason. It is the only moon in the solar system with a thick atmosphere, and it is one of the most Earth-like worlds we have ever studied, despite being unimaginably cold. Titan's atmosphere is mostly nitrogen, just like Earth's, with a small amount of methane and traces of other hydrocarbons. The atmosphere is so thick that the surface pressure is about 50% higher than Earth's at sea level. This thick atmosphere creates a greenhouse effect, though Titan is still far too cold for liquid water. The average surface temperature is about minus 179 degrees Celsius. The methane in Titan's atmosphere plays a role similar to water on Earth. It evaporates from the surface, forms clouds, and falls as rain. There are rivers, lakes, and seas on Titan, but they are made of liquid methane and ethane, not water. These hydrocarbon lakes are mostly found near the poles, where the temperature is slightly lower and the evaporation rate is slower. The largest of these seas, Kraken Mare, is bigger than the Caspian Sea on Earth. The lakes are smooth and calm, with very little wave activity, though the wind does occasionally create ripples. Titan's surface is hidden beneath a thick orange haze, a smog made of complex organic molecules created by sunlight breaking apart methane in the upper atmosphere. This haze is so thick that the surface is invisible in ordinary light, but radar and infrared observations have revealed a diverse landscape, with mountains, valleys, dunes, and impact craters. The dunes are particularly interesting. They are made of small grains of ice and hydrocarbons, and they are shaped by the wind, which blows mostly from west to east. The dunes are hundreds of kilometers long and over 100 meters tall, similar in size to the sand dunes in the Sahara Desert. Titan also has cryovolcanoes, volcanoes that erupt with water and ammonia instead of molten rock. These cryovolcanoes may be active, though this is still uncertain. If they are active, they would be replenishing Titan's atmosphere with methane, which is constantly being destroyed by sunlight. Without some source of methane, Titan's atmosphere would disappear over millions of years, so there must be a reservoir of methane somewhere, either in the interior or on the surface. Beneath Titan's icy crust, there may be a subsurface ocean of liquid water. This ocean would be kept liquid by heat from the moon's interior, possibly generated by tidal forces from Saturn's gravity. If this ocean exists, it could be dozens of kilometers deep, and it might even contain the ingredients for life, though the conditions would be very different from anything on Earth. The narrative continues exploring Titan's underground ocean and organic chemistry, then moves through Saturn's diverse moon system, including Enceladus with its ice geysers and subsurface ocean, Mimas with its Death Star crater, Iapetus' two-tone appearance, Rhea, Dione, Tethys, Hyperion's chaotic tumbling, and smaller moons. It then describes Saturn's magnetosphere, auroras, radio emissions, seasonal changes including the 2009 equinox ring plane crossing, and the Cassini mission's discoveries from 2004 to 2017, including its grand finale orbits between Saturn and its rings before plunging into the planet's atmosphere. The discoveries Cassini made during those final orbits remain among the most remarkable in planetary science. As the spacecraft passed between Saturn and its innermost ring edge, just 2,000 kilometers above the cloud tops, it sampled the planet's upper atmosphere directly for the first time. The instruments detected complex organic molecules falling from the rings into the atmosphere, creating a gentle rain of particles that had orbited the planet for millions of years. This connection between rings and planet, this exchange of material across the gap, revealed how deeply intertwined these two systems truly are. The spacecraft also measured Saturn's gravitational field with unprecedented precision during those close passes. These measurements allowed scientists to peer inside the planet, determining how mass is distributed within its interior. The data showed that Saturn's core is larger and more diffuse than previously thought, perhaps not a distinct solid sphere, but a gradient of heavier elements mixed with hydrogen and helium, slowly transitioning from the center outward. This understanding changed how we think about giant planet formation, suggesting that these worlds assembled their cores while simultaneously gathering their massive atmospheres, rather than building a core first and adding gas later. The magnetic field measurements from a grand finale revealed another surprise. Saturn's magnetic field is remarkably well aligned with its rotation axis, more so than any other planet in the solar system. Earth's magnetic field is tilted about 11 degrees from its rotation axis, and most other planets show similar or greater tilts. But Saturn's magnetic field is aligned to within less than 1 degree, so precisely centered that it initially seemed almost impossible. This alignment creates a puzzle for planetary scientists, because magnetic fields are generated by flowing, conducting fluids inside planets, and such flows typically create fields that are offset or tilted. The mechanism that keeps Saturn's field so perfectly aligned remains one of the planet's enduring mysteries. Beyond what Cassini discovered, there is something deeply calming about simply knowing what Saturn is made of at the most fundamental level. If you could somehow gather all of Saturn's mass and separate it into its constituent elements, you would find that about 96% of his hydrogen and helium, the two lightest elements, the same materials that make up most of the Sun and most of the universe. The remaining 4% consists of heavier elements, what astronomers call metals regardless of their actual chemical nature. These include water, methane, ammonia, and traces of many other compounds. Saturn is, in essence, a collection of the universe's most common materials, arranged by gravity into a sphere spinning quietly in the outer solar system. The hydrogen inside Saturn exists in forms that we never encounter on Earth. Near the surface, it behaves as a normal gas, the same molecular hydrogen that fills balloons or powers fuel cells. But as you descend into the planet, pressure and temperature increase, and the hydrogen gradually changes. At a depth of about 30,000 kilometers, the pressure becomes so intense that hydrogen molecules are squeezed together until they break apart, and the individual atoms merge into a liquid metal. This metallic hydrogen conducts electricity like copper or iron, and it flows in vast currents driven by the planet's internal heat and rotation. These flowing currents generate Saturn's magnetic field, creating an invisible shield that extends millions of kilometers into space. The transition from molecular to metallic hydrogen is not abrupt. There is no sharp boundary, no surface where one form ends and the other begins. Instead, there's a gradient, a gradual shift over thousands of kilometers where the hydrogen slowly changes its nature. This smooth transition is part of what makes Saturn such a peaceful object to contemplate. There are no violent boundaries inside this planet, no colliding layers or sudden discontinuities, just gentle gradations of pressure, temperature, and phase, all held in balance by gravity. Saturn's internal heat, is another source of quiet fascination. The planet radiates about twice as much energy into space as it receives from the sun. This extra heat does not come from nuclear fusion, as in a star, nor from radioactive decay, as in Earth's interior. Instead, it comes from a slow, gentle process called helium differentiation. Deep inside Saturn, helium droplets condense out of the hydrogen-helium mixture and slowly rain downward toward the core. As these droplets fall through the metallic hydrogen layer, they release gravitational potential energy, which is converted into heat. This process has been continuing for billions of years, and it will continue for billions more, a patient internal engine that keeps Saturn warmer than it would otherwise be. This internal warmth has profound effects on Saturn's atmosphere. The heat rising from the interior drives convection currents, creating the bands and zones we see in the cloud tops. Warm gas rises in the bright zones, cools at altitude, and sinks in the darker bands, creating circulation cells that stretch around the entire planet. These convection cells are stable over long periods, maintaining their structure year after year, though the winds within them can reach extraordinary speeds. The internal heat also means that Saturn's weather is driven more by heat from below than by sunlight from above, unlike Earth's weather, which is primarily solar-powered. The long-term stability of Saturn's atmosphere is remarkable. While storms come and go, and the great white spots appear once per Saturnian year, the overall structure of the atmosphere remains consistent. The bands maintain their positions, the winds blow in the same directions at the same speeds, and the temperature gradients stay roughly constant. This stability suggests that Saturn's atmosphere is in a kind of equilibrium, a balance between the heat rising from below, the cooling of upper layers to space, and the planet's rapid rotation. It is a system that has found its rhythm and maintains it across the centuries. Saturn's seasons, though subtle, do create measurable changes. As different hemispheres tilt toward the sun during the planet's long year, the temperature differences between north and south shift gradually. These temperature changes affect cloud formation, wind speeds, and storm activity. The hexagon at the North Pole changes color with the seasons, appearing more golden during summer and fading during winter, likely due to changes in the photochemical reactions that occur when sunlight strikes the upper atmosphere. These seasonal shifts are slow and gentle, taking years to develop. Nothing sudden or violent, just the patient response of a massive atmosphere to the changing angle of distant sunlight. The rings, too, respond to Saturn's seasons. As the planet orbits the sun, the rings are illuminated from different angles, and twice each Saturnian year, the sun passes through the ring plane, an event called an equinox. During equinox, the rings cast almost no shadow on the planet, and the planet casts almost no shadow on the rings. Sunlight strikes the ring's edge on, illuminating only the highest peaks and structures. These moments reveal vertical features in the rings that are otherwise invisible, such as the towering walls of the Keeler Gap created by Daphnis, which can extend several kilometers above the ring plane. Observing Saturn during equinox is like watching a familiar landscape at sunset, when long shadows reveal details that are hidden in full daylight. The way sunlight interacts with the rings is endlessly fascinating. Because the ring particles are made mostly of water ice, they reflect sunlight very efficiently, especially at visible wavelengths. This is why Saturn's rings are so bright, far brighter than the planet itself. Ice is one of the most reflective natural substances, and when billions of ice particles are spread across hundreds of thousands of kilometers, they create a mirror that catches and scatters sunlight across the solar system. Spacecraft approaching Saturn can see the reflected light from the rings long before the planet itself becomes visible, a glowing herald announcing the presence of this remarkable world. The rings also reflect light in different ways depending on the viewing angle. When you look at the rings with the sun behind you, they appear bright and opaque, because the ice particles scatter sunlight back toward you. But when you look at the rings with the sun behind them, they appear darker and more transparent because much of the light passes through the gaps between particles. This effect, called forward scattering versus back scattering, allows scientists to learn about the size and spacing of ring particles by observing how the ring's brightness changes with viewing geometry. Cassini used this technique extensively, watching stars pass behind the rings and measuring how their light was dimmed and scattered, creating detailed maps of ring structure. One of the most beautiful phenomena in Saturn's system is the way the rings cast shadows on the planet. Because the rings are so broad and the sun is so distant, the shadow is a sharp, dark band that stretches across Saturn's globe, moving with the seasons as the planet's tilt changes. When the northern hemisphere is tilted toward the sun, the shadow falls across the southern hemisphere, and vice versa. This shadow is not just a visual feature. It affects the temperature of the atmosphere beneath it, cooling the shadowed regions and creating subtle changes in wind patterns and cloud formation. The rings, in this way, influence the planet they orbit, a quiet interaction between two parts of a single system. The rings also create another kind of shadow, one that is less visible but equally important. They block some of the sunlight that would otherwise reach Saturn's upper atmosphere, reducing the amount of solar energy available to drive photochemical reactions. This shadowing effect is strongest near the equator, where the rings pass directly overhead, and it varies with the seasons as the planet's tilt changes. Scientists are still studying how this shadowing affects the chemistry of Saturn's atmosphere, but it is clear that the rings and the planet are not separate entities. They are parts of an interconnected system, each influencing the other in subtle ways. Beyond the rings and the planet, Saturn's magnetosphere creates another layer of interaction. The magnetosphere is the region of space dominated by Saturn's magnetic field, extending millions of kilometers outward from the planet. Within this region, charged particles from the solar wind are deflected and trapped, creating radiation belts similar to Earth's Van Allen belts. These trapped particles spiral along magnetic field lines, bouncing between the planet's northern and southern hemispheres, and they interact with Saturn's moons and rings as they orbit through the magnetosphere. The rings themselves have a profound effect on the magnetosphere. As ring particles are bombarded by meteoroids or eroded by ultraviolet light, they release water molecules and ions into the surrounding space. These particles are picked up by Saturn's magnetic field and become part of the planet's ionosphere and magnetosphere. This process creates a vast, diffuse cloud of water-derived ions that surround Saturn, extending far beyond the visible rings. Cassini detected this cloud and measured its composition, finding that it contains not just water ions, but also molecular oxygen and other species created when water molecules are broken apart by radiation. The interaction between the magnetosphere and Saturn's moons is equally complex. Enceladus, with its powerful geysers, injects hundreds of kilograms of water vapor into space every second. This water quickly breaks apart into ions and electrons, which are swept up by Saturn's magnetic field and spread around the planet, creating a vast torus of material that orbits Saturn at the same distance as Enceladus. This torus is invisible to the eye, but spacecraft instruments can detect it through its effect on the magnetic field and by observing the ultraviolet light emitted when the ions recombine. The torus is constantly replenished by Enceladus and constantly lost as particles are absorbed by other moons or escape the magnetosphere, a dynamic equilibrium that has persisted for as long as Enceladus has been geologically active. Titan also interacts with Saturn's magnetosphere, but in a different way. Titan has a thick atmosphere that extends high above its surface, and this atmosphere is constantly being stripped away by the solar wind and Saturn's magnetospheric plasma. The interaction creates a wake behind Titan, a region where the magnetic field is disturbed and charged particles are accelerated. This wake can be detected by spacecraft passing through it, and it provides clues about the composition and density of Titan's upper atmosphere. Over billions of years, this process has removed a significant portion of Titan's original atmosphere, though the moon's interior continues to release new gases through cryovolcanism and outgassing, maintaining the atmosphere we see today. Saturn's magnetosphere also generates radio emissions, a kind of natural radio signal that can be detected by spacecraft and even, under rare circumstances, by radio telescopes on Earth. These emissions are created when charged particles spiral along magnetic field lines and emit radiation, a process called synchrotron emission. The radio signals vary with Saturn's rotation period, and for many years, scientists used these variations to measure how fast Saturn spins. But the discovery that Saturn's magnetic field is so precisely aligned with its rotation axis complicated this measurement, because the radio emissions no longer provide a clear, unambiguous rotation period. This puzzle remains one of the open questions in Saturnian science. The auroras at Saturn's poles are another manifestation of the magnetosphere's activity. Like Earth's auroras, Saturn's are created when charged particles from the magnetosphere are funneled down magnetic field lines into the upper atmosphere, where they collide with gas molecules and cause them to glow. Saturn's auroras emit light primarily in the ultraviolet, though they also produce some visible and infrared light. They are not as bright or as variable as Earth's auroras, but they are persistent, glowing steadily at both poles. The auroras change in response to the solar wind and to the rotation of Saturn's magnetosphere, creating patterns that shift and pulse over hours and days. Cassini observed Saturn's auroras extensively, using ultraviolet cameras to capture images of the glowing rings of light at the poles. These observations revealed that Saturn's auroras are influenced not just by the solar wind, but also by the planet's moons, particularly Enceladus. When the magnetosphere rotates past Enceladus and encounters the plume of water vapor, the interaction creates disturbances in the magnetic field that propagate along field lines to the poles, brightening the auroras. This connection between a moon's geological activity and the planet's auroral displays is unique in the solar system, a beautiful example of how different parts of the Saturnian system are interconnected. The color of Saturn itself is another calming detail. Unlike Jupiter, with its vivid oranges, reds, and browns, Saturn appears in shades of pale gold, cream, and soft amber. This coloration comes from the same basic atmospheric chemistry as Jupiter, with ammonia ice crystals forming the upper cloud layer and deeper clouds of ammonium hydrosulfide and water below. But Saturn's colors are more muted, partly because the planet is colder and the clouds form at higher altitudes, and partly because a high-altitude haze of photochemical smog scatters blue light, giving the planet its warm, golden hue. This haze is made of complex organic molecules created when sunlight breaks apart methane and other hydrocarbons in the upper atmosphere, and the particles slowly drift downward, adding to the planet's soft appearance. The clouds on Saturn are layered in a way that creates subtle variations in color and brightness. The uppermost layer, made of ammonia ice, is white or pale cream. Below that, at higher pressures and temperatures, clouds of ammonium hydrosulfide form, adding shades of yellow and brown. Deeper still, where temperatures reach the freezing point of water, clouds of water ice and liquid water droplets exist, though these are rarely visible from space because they are obscured by the layers above. This vertical structure creates a stratified atmosphere where different chemical processes occur at different altitudes, each contributing to the planet's overall appearance. The way Saturn's atmosphere scatters light also contributes to its appearance. The thick haze in the upper atmosphere scatters shorter wavelengths of light more than longer wavelengths, a process called Rayleigh scattering, the same process that makes Earth's sky blue. But on Saturn, the haze particles are larger and more complex, so they scatter light less selectively, creating a softer, more diffuse glow. This scattering gives Saturn a slightly blurred appearance, as if the planet is wrapped in a thin veil, softening the edges of clouds and bands and giving the whole world a gentle, dreamlike quality. Saturn's rotation, though rapid, is not uniform throughout the planet. Different latitudes rotate at different speeds, a phenomenon called differential rotation. The equator completes a rotation in about 10 hours and 14 minutes, while higher latitudes take slightly longer. This differential rotation is possible because Saturn is a fluid body, not a solid one, and different parts of the atmosphere can move independently. The differential rotation creates shear between adjacent latitude bands, and this shear drives the formation of the jet streams that define the boundaries between bands. The interaction between rotation, convection, and shear creates the complex atmospheric dynamics we observe, a balance of forces that has persisted for billions of years. The way we measure Saturn's rotation period has changed over time. Early astronomers measured it by watching clouds move across the planet's disk, but this method gave different results at different latitudes because of differential rotation. Later, scientists used radio emissions from the magnetosphere, which rotate with the planet's interior, to determine a more fundamental rotation period. But the discovery that Saturn's magnetic field is so precisely aligned with its rotation axis meant that the radio emissions no longer varied in a simple way, making it difficult to measure the rotation period precisely. Recent studies have used subtle variations in the gravitational field measured by Cassini to estimate the rotation period of Saturn's deep interior, finding a value of about 10 hours and 33 minutes, though this measurement is still uncertain. The uncertainty about Saturn's exact rotation period is a reminder that even after decades of study and a 13-year orbital mission, there are still basic questions about this planet that remain unanswered. Saturn is not a simple object, and its complexity continues to reveal itself the more closely we look. This sense of ongoing discovery, of questions that remain open, is part of what makes Saturn such a compelling subject. It is not a world that has been fully cataloged and understood. It is a world that continues to surprise us, gently and patiently, with each new observation. One of the most surprising discoveries from Cassini's mission was the detection of a faint, diffuse ring far beyond the main ring system, associated with the moon Phoebe. This ring, called the Phoebe ring, is enormous, extending from about 6 million kilometers to more than 12 million kilometers from Saturn, making it by far the largest ring in the solar system. The Phoebe ring is so diffuse and dark that it was not discovered until 2009, when the Spitzer Space Telescope detected its faint infrared glow. The ring is made of dust particles knocked off Phoebe by micrometeorite impacts, and these particles slowly spiral inward towards Saturn over millions of years. The Phoebe ring is aligned with Phoebe's orbit, which is tilted 27 degrees from Saturn's equator and is retrograde, meaning Phoebe orbits in the opposite direction from most of Saturn's moons. This unusual orbit suggests that Phoebe is a captured object, likely a Kuiper belt body that was gravitationally captured by Saturn early in the solar system's history. The Phoebe ring, then, is made of material from the outer solar system, ancient dust that has been orbiting Saturn for billions of years. This ring is so large that if you could see it from Earth, it would appear many times larger than the full moon, though it is far too faint to be visible without sensitive infrared instruments. The discovery of the Phoebe ring also solved a long-standing mystery about Iapetus, Saturn's third largest moon. Iapetus has a striking two-toned appearance, with one hemisphere bright white and the other dark brown, almost black. For centuries, astronomers wondered what could cause such a stark contrast. The discovery of the Phoebe ring provided the answer. The dark material on Iapetus is dust from the Phoebe ring, which slowly spirals inward and is swept up by Iapetus as the moon orbits through it. The dust accumulates on Iapetus' leading hemisphere, the side that faces forward in its orbit, darkening it over time. The bright trailing hemisphere remains covered in clean water ice, creating the dramatic contrast we observe. This connection between Phoebe, its ring, and Iapetus is another example of how Saturn's moons interact and influence each other across vast distances. The way Saturn's system has evolved over billions of years is a story of slow, patient change. The rings are gradually losing material, raining down onto the planet and spreading outward into space. The moons migrate slowly in their orbits, their positions shifting due to tidal interactions with Saturn. Enceladus and Titan continue to release material into space, feeding Saturn's magnetosphere and creating diffuse rings and tori. The planet itself continues to radiate heat from its interior, driving atmospheric circulation and maintaining the bands and storms we observe. All of these processes operate on timescales far longer than human lifetimes. Yet they are not static. They are dynamic, evolving, changing in ways that we can measure and predict. One of the most calming aspects of studying Saturn is the realization that these processes will continue long after we are gone. The rings will continue to orbit, the moons will continue to circle the planet, the storms will continue to swirl in the atmosphere, and the magnetosphere will continue to deflect the solar wind. Saturn does not need us to observe it or understand it. It simply exists, following the laws of physics, a patient presence in the outer solar system. Our observations and our curiosity do not change Saturn. They only change us, expanding our understanding and deepening our appreciation for the complexity and beauty of the universe. The scientific study of Saturn has also revealed how much we can learn from a single planetary system. Saturn and its moons provide examples of almost every major process in planetary science: atmospheric dynamics, ring formation and evolution, tidal heating, cryovolcanism, magnetospheric interactions, moon formation, orbital resonances, and more. By studying Saturn, we learn principles that apply to other planets, other moons, and even exoplanetary systems around distant stars. Saturn is not just an object of study in itself. It is a laboratory, a natural experiment that allows us to test our theories and refine our understanding of how planetary systems work. The images of Saturn captured by Cassini and other spacecraft have also had a profound cultural impact. These images, showing the planet in exquisite detail, the rings in all their complexity, and the moons in their strange and wonderful variety, have inspired countless people to look up at the night sky in wonder. They have reminded us that we live in a universe of extraordinary beauty and complexity, and that there are worlds beyond our own that are worth exploring and understanding. The images of Saturn are not just scientific data. They are works of art, capturing moments of cosmic beauty that resonate with something deep in the human spirit. There is a particular image from Cassini's mission that has become iconic, known as the Day the Earth Smiled. On July 19, 2013, Cassini turned its cameras back toward the inner solar system and captured an image of Saturn backlit by the sun, with the rings glowing in forward scattered light. In that image, barely visible as a tiny pale blue dot, is Earth, nearly 1.5 billion kilometers away. This image, showing our entire world as a single pixel in a vast cosmic scene, is a powerful reminder of our place in the universe. It shows that Earth, with all its complexity and all its life, is just one small part of a much larger system, a single world among many, orbiting an ordinary star in an ordinary galaxy. The perspective that Saturn provides, both literally and figuratively, is humbling and calming. It reminds us that the universe is vast, that time is long, and that the processes that shape planets and moons operate on scales far beyond our everyday experience. It reminds us that we are part of something much larger than ourselves, connected to the cosmos through the same physical laws that govern Saturn's rings, Titan's atmosphere, and Enceladus's geysers. This perspective does not diminish us. It enriches us, giving us a sense of context and connection that is deeply meaningful. As we continue to explore Saturn, new questions arise and old questions find new answers. Future missions may return to the Saturnian system, perhaps to orbit Titan or to land on Enceladus, searching for signs of life in the subsurface oceans of these remarkable moons. Telescopes on Earth and in space will continue to observe Saturn, tracking the changes in its atmosphere, its rings, and its magnetosphere. Each new observation adds to our understanding, filling in details and revealing new mysteries. The study of Saturn is not complete. It is ongoing, a patient accumulation of knowledge that will continue for generations. The technology that allows us to study Saturn has advanced dramatically over the past few decades. The first images of Saturn, captured by Pioneer 11 in 1979, were grainy and low resolution, showing the planet and rings as little more than bright shapes against the darkness of space. The Voyager flybys in 1980 and 1981 provided much better images, revealing the ring's structure and discovering new moons. But it was Cassini, arriving in 2004 and orbiting for 13 years, that truly opened Saturn to detailed study. Cassini's cameras, spectrometers, and other instruments provided data of unprecedented quality and quantity, transforming our understanding of the Saturnian system. The data from Cassini will be analyzed for decades to come. The mission returned so much information, covering so many aspects of Saturn and its moons, that scientists are still discovering new results years after the mission ended. This long tail of scientific productivity is characteristic of major space missions. The data they return continues to yield insights long after the spacecraft themselves are gone. Cassini's final plunge into Saturn's atmosphere in September 2017 was the end of the spacecraft, but it was not the end of the mission's contributions to science. The way Cassini ended its mission was both poignant and practical. After 13 years in orbit, the spacecraft was running low on fuel, and mission controllers needed to ensure that it would not accidentally crash into one of Saturn's moons, particularly Enceladus or Titan, which might harbor life. To prevent any possibility of contaminating these moons with Earth microbes that might have survived on the spacecraft, the mission team chose to send Cassini into Saturn's atmosphere, where it would burn up completely. The final orbits, passing between the planet and the rings, provided some of the mission's most valuable data, and the spacecraft transmitted information until the very last moment, as it descended into the thickening atmosphere and lost contact with Earth. The data Cassini sent back continues to reveal new patterns even now, years after the spacecraft itself is gone. Scientists still work through the measurements, finding subtle details in the way particles moved, in the composition of molecules sampled during those final orbits, in the magnetic field variations recorded as the spacecraft passed through regions no probe had ever visited before. Each discovery adds another layer to our understanding, another piece of the intricate puzzle that is Saturn and its rings. And there are questions still waiting. Future missions may one day return to Saturn, carrying instruments designed to answer what Cassini could not. Proposals exist for orbiters that would study the rings in even greater detail, for landers that might touch down on moons like Enceladus or Titan, for probes that could sample the water plumes directly or dive into Titan's methane seas. These missions live in blueprints and presentations for now, waiting for the resources and commitment that space exploration requires. But the knowledge Cassini provided makes each future mission more focused, more capable of finding what we most want to know. One concept envisions a spacecraft that would orbit Enceladus specifically, passing repeatedly through its plumes to analyze the chemistry of the subsurface ocean in far greater detail than Cassini's brief flybys allowed. Such a mission could determine not just what molecules are present, but in what concentrations, in what combinations, with what energy states. It could search for the specific chemical signatures that might indicate biological processes, or at least the conditions where such processes could occur. The moon's geysers offer a rare gift in planetary science, a way to sample an ocean without drilling through kilometers of ice. Another proposal focuses on Titan. With a lander or even a floating probe, it could drift on one of the methane lakes, measuring currents and chemistry, watching the weather, studying the shorelines where liquid meets solid in an alien echo of Earth's own coastlines. Some designs include aerial vehicles that could fly through Titan's thick atmosphere, covering distances impossible for a stationary lander, imaging the surface in detail, perhaps even witnessing a methane rainstorm as it falls and flows and carves the landscape. The rings themselves remain a target of intense interest. Future missions might carry instruments capable of measuring the exact ages of ring particles, resolving the debate about whether the rings are ancient or recent. They might map the ring's thickness variations with precision, track individual particles over time, or study the countless moonlets embedded in the ring structure. Each ring holds stories written in the distribution of its particles, in the waves that ripple through it, in the gaps and braids and spirals that gravity creates. Saturn's magnetosphere also calls for deeper study. Its interactions with the solar wind, with the moons, with the rings create a complex electromagnetic environment that we have only begun to understand. The auroras that dance around Saturn's poles respond to these interactions in ways that reveal the planet's internal structure and the nature of its magnetic field. Future missions might include magnetometers and particle detectors capable of mapping this environment in 3 dimensions over time, watching how it changes with the seasons and with solar activity. The planet's interior remains largely mysterious despite everything Cassini revealed. We know now that the core is diffuse rather than solid, that metallic hydrogen fills much of the interior, that helium rain falls through the depths. But the exact boundaries between these layers, the precise conditions at each depth, the way heat flows from the interior to the surface, these details still elude us. Seismology, the study of waves moving through a planet's interior, could reveal this structure the way it has for Earth. A future mission might listen for Saturn quakes, measuring the vibrations that pass through the planet and using them to map what lies within. And beyond Saturn, the other giant planets wait with their own ring systems and mysteries. Jupiter's faint rings, discovered by Voyager, remain poorly understood. Uranus and Neptune, visited only once by Voyager 2 in brief flybys decades ago, have rings that we have barely glimpsed. Each system offers variations on the themes Saturn plays so magnificently, each one a laboratory where gravity and motion create structure from chaos. The study of planetary rings extends beyond our own solar system now. Astronomers have found evidence of rings around exoplanets, worlds orbiting other stars. Though we cannot yet image these rings directly, we infer their presence from the way starlight dims and changes as these distant worlds pass in front of their suns. Some of these ring systems may dwarf Saturn's, extending millions of kilometers into space. Others might be made of materials we have never encountered, shaped by conditions utterly unlike those in our solar system. Saturn's rings give us a foundation for understanding these distant systems, a reference point in the vast diversity of planetary architecture. There is something profoundly calming in knowing that Saturn continues its ancient dance whether we watch or not. The rings orbit, the moons circle, the seasons turn with the slow patience of a world where a year lasts 30 Earth years. The hexagon at the North Pole maintains its shape. The storms swirl and dissipate and form again. The particles in the rings collide and separate in an endless, gentle ballet. Nothing there hurries. Nothing there rushes toward conclusion. This steadiness offers a kind of comfort. In a universe of violent events, stars exploding, galaxies colliding, black holes consuming everything near them, Saturn represents stability and grace. Its changes unfold over timescales that make human lifetimes seem like brief moments. The rings that shine tonight shone for ancient civilizations, for dinosaurs, for the first life that crawled from Earth's oceans. They will shine, though diminished, for generations yet unborn, slowly raining down onto the planet in a process so gradual that no single human lifetime could perceive it. We find beauty in this permanence, in the way some things persist while others change. Saturn reminds us that the universe contains both, the explosive and the serene, the sudden and the gradual, the violent and the peaceful. The rings exist in a state of dynamic equilibrium, constantly changing in detail, but stable in overall structure, a pattern that emerges from countless small interactions and persists across ages. The science of Saturn connects to broader questions about how planets form, how solar systems evolve, how the raw materials of the universe organize themselves into the structures we see. The rings are not separate from this story. They are part of it. A chapter about what happens when gravity and motion interact with fields of small particles. The same physics that shapes Saturn's rings operates in the disks around young stars where planets are forming, in the accretion disks around black holes, and the spiral arms of galaxies. Understanding Saturn helps us understand these other systems, these other scales of cosmic architecture. And there is something deeply human in our desire to understand these distant places. We send spacecraft across billions of kilometers, wait years for them to arrive, then watch the data return at the speed of light, still taking over an hour to cross the gap between Saturn and Earth. We build instruments of extraordinary precision, write software of great complexity, coordinate the efforts of thousands of people across decades, all to learn about a world we will likely never touch, rings we will never walk among, moons we will never stand upon. This effort speaks to something essential in human nature: curiosity, wonder, the need to know what lies beyond the horizon. Saturn satisfies this need while generating more questions, each answer revealing new mysteries, each discovery opening new avenues of inquiry. The more we learn, the more we find to learn. The more we understand, the more we appreciate the complexity and beauty of what we are trying to understand. For those falling asleep to these words, Saturn offers a gentle subject for the mind to rest upon. Its vast distances create a sense of space and calm. Its slow movements suggest patience and peace. Its rings, made of countless separate pieces that somehow form a coherent whole, mirror the way individual thoughts and impressions form the coherent experience of consciousness. As sleep approaches, thoughts fragment and drift like ring particles, each one separate yet part of a larger pattern, each one reflecting light in its own way. You might imagine yourself drifting above those rings, weightless and calm, watching the particles stream past in their orbits. Each piece of ice catches the distant sunlight, glows softly, then passes into shadow. The view extends in all directions, the rings curving away toward horizons impossibly far, the planet filling half the sky with its serene presence, the stars beyond shining steady and clear in the absence of any atmosphere to make them twinkle. In this imagined place, there is no up or down, no urgency, no schedule to keep. You float in the silence of space, where sound cannot travel, where the only motion is the slow orbit of everything around the planet far below. Time moves differently here. An hour might feel like a moment, or a moment like an hour. The distinction ceases to matter in the face of such vastness, such quiet, such peace. The rings stretch out beneath you, detailed beyond imagination when you focus on any small section. yet simple in their overall structure when you pull back to see the whole. This shift in perspective, from the particular to the general, from the detailed to the broad, mirrors the way consciousness moves as sleep approaches. The sharp focus of waking thought softens. Individual concerns blend into general feelings. The boundaries between ideas become less distinct. Saturn's moons pass in their orbits, each one a world with its own character, its own story. Titan glows orange through its haze. Enceladus gleams white and clean, its geysers invisible from this distance, but present nonetheless, spraying water into space in a constant gentle fountain. Mimas shows its giant crater, Iapetus its two-tone surface, Rhea its ancient ice. They move in silence, patient, following paths determined billions of years ago, paths they will follow for billions of years to come. There is no danger here in this imagined space, no cold that can harm you, no vacuum to fear. This is a place of pure observation, pure presence, where you can simply exist and watch and let the immensity of it all wash over you like a gentle tide. The scale of Saturn, its size, its distance, its age, puts human concerns into a perspective that can be oddly comforting. The worries that seem so large in daily life shrink when held against the backdrop of a planet with a diameter of 120,000 kilometers, rings that extend for hundreds of thousands of kilometers more, a system that has existed for most of the history of the solar system. This is not to say that human concerns do not matter. They do, deeply and truly. But sometimes the mind needs to step back, to see from a distance, to remember that the universe is vast and ancient, and that we are part of it, connected to it through the same physical laws that shape Saturn's rings and guide its moons. The atoms in your body were forged in stars, scattered through space, gathered into the cloud that became our solar system. You are made of the same materials as Saturn, as its rings, as its moons. The difference is only in arrangement, in the particular pattern those atoms have taken. As sleep draws closer, these thoughts can blur and soften. The details of ring structure, the names of moons, the numbers that describe orbits and masses, all of this can fade into a general sense of wonder and peace. What remains is the feeling of connection, of being part of something larger, of existing in a universe that contains such beauty and such mystery. Saturn will be there tomorrow, and the day after, and for all the days of your life, and far beyond. The rings will continue their slow orbit. The moons will follow their paths. The seasons will turn on a world where each season lasts more than 7 Earth years. This continuity, this persistence, this patient unfolding of pattern and structure, these offer a kind of anchor, a reminder that some things endure, some things remain, some things continue regardless of the small turbulences of daily existence. And if you're still awake, still listening, there are more stories to tell. The universe is full of them. Each planet has its character, each moon its mysteries, each star its story. Beyond our solar system, galaxies spiral and cluster, nebulae glow with the light of newborn stars. Black holes warp space-time itself into shapes that challenge imagination. All of this exists right now, while you lie in darkness listening to these words. All of it continues, vast and ancient and beautiful. But Saturn, with its rings, holds a special place in human imagination. It is the planet that looks like no other, the one that announced itself to Galileo's primitive telescope as something strange and wonderful, the one that has rewarded every improvement in our instruments with new details and new mysteries. It is far enough to seem exotic, yet close enough that we can study in detail. It is large enough to dominate its region of the solar system, yet gentle in its appearance, lacking the stormy violence of Jupiter or the extreme tilts of Uranus and Neptune. The rings make Saturn recognizable even to those who know little astronomy. Show a picture of Saturn to almost anyone, and they will know what they are seeing. This familiarity breeds a kind of affection. Saturn becomes not just an object of scientific study, but a presence in human culture, appearing in art and literature, in films and dreams, in the imaginations of children who look up at the night sky and wonder what lies beyond the visible stars. Those rings, so thin and so vast, so fragile and so enduring, capture something essential about the universe itself. That complexity can arise from simple rules, that beauty can emerge from physics, that order and chaos can coexist in the same system. The rings are chaotic in their details. Each particle follows its own path, collides with its neighbors, responds to countless gravitational tugs from moons and planet and other particles. Yet from this chaos comes order. The clear division into rings, the gaps that open and persist, the waves that propagate through the particle field like ripples on a pond. This emergence of order from chaos appears throughout nature. It is how galaxies form their spiral arms, how sand dunes organize themselves in irregular patterns, how snowflakes grow their intricate symmetries. It is a fundamental principle of how the universe works, and Saturn's rings demonstrate on a scale we can observe and measure and begin to understand. Each ring particle is simple, just a chunk of ice, perhaps with some rock mixed in, following the basic laws of motion and gravity. But billions of these simple particles, interacting over millions of years, create something magnificent. As your thoughts drift toward sleep, you might hold this image, a single particle of ice, no larger than a pebble, orbiting Saturn in the company of countless others. It has orbited for thousands of years, perhaps millions, colliding gently with its neighbors, reflecting sunlight, moving through shadow and light as it circles the planet. It will continue for thousands or millions of years more, part of a system so large that no human mind can fully grasp it, yet simple enough in its basic nature that we can understand the physics that governs it. That particle knows nothing of its place in the grand structure. It simply exists, following the path that gravity and momentum dictate, responding to each collision, each gravitational tug, each subtle force that acts upon it. Yet it is part of something beautiful, something that has inspired wonder for as long as humans have been able to see it. Its existence matters not because of what it knows or intends, but simply because it is part of the pattern, part of the whole, part of the great ring system that encircles Saturn. In the same way, each of us is part of larger patterns we may not fully perceive. We move through our lives, responding to forces we understand and forces we do not, colliding gently with those around us, following paths shaped by gravity, both literal and metaphorical. And somehow, from all these individual paths, patterns emerge, societies, cultures, histories, the great human story that unfolds across generations. We are each like a ring particle, small in ourselves, but part of something larger, something that has beauty and meaning in its overall structure, even when we cannot see it from our individual perspective. This thought, too, can be comforting as sleep approaches. You do not need to understand everything, to see the whole pattern, to know your exact place in the grand scheme. You can simply exist, simply be, simply follow your path with whatever grace you can manage, trusting that somehow it all fits together, that somehow meaning emerges from the countless small actions and interactions that make up a life. Saturn teaches patience. Its year is 30 Earth years long. Its rings formed slowly, perhaps from a moon that wandered too close and was torn apart, perhaps from material that never coalesced into a moon in the first place. Either way, the process took time, not days or years, but epochs. The rings we see now are not the rings that existed a billion years ago, and they will not be the rings that exist a billion years hence. They change, but so slowly that from any human perspective they seem eternal. This patience extends to our study of Saturn. We have observed it for 4 centuries, sent 4 spacecraft to visit it, orbited it for 13 years with Cassini. Yet we have only begun to understand it. Each answer leads to new questions. Each measurement reveals new complexities. We will be studying the data Cassini returned for decades to come, and even then we will not know everything. There will still be mysteries, still be questions, still be reasons to return. And that is as it should be. The universe is not meant to be fully known in a single lifetime, or even in the lifetime of a civilization. It is vast beyond measure, complex beyond full comprehension, ancient beyond human timescales. We learn what we can, we discover what we are able, we push the boundaries of knowledge outward bit by bit. But there will always be more to learn, more to discover, more to wonder about. This infinity of knowledge need not be frustrating. It can be freeing. There is no final exam, no point at which you must know everything. You can learn at your own pace, follow your own curiosity, rest when you need to rest. The universe will wait. Saturn will wait. The rings will continue their orbit whether you understand them completely or only appreciate their beauty from afar. For now, as sleep comes closer, it is enough to know that Saturn exists, that its rings shine in the night sky even when we cannot see them, that its moons follow their ancient paths, that somewhere out there in the darkness of space, a giant world of gas and liquid spins with its crown of ice and rock, patient and serene. It is enough to have touched, even briefly, the wonder of it, to have let your mind wander among those distant moons and through those vast rings, to have imagined the view from that alien sky. The details will fade as sleep takes hold. The numbers and names will slip away. The specific facts blur into general impressions. But something will remain, a sense of the vastness of space, the beauty of natural law, the patience of cosmic time. These things will settle into your sleeping mind like sediment drifting down through still water, becoming part of the foundation of thought, the bedrock of understanding upon which tomorrow's consciousness will build. And if some part of you dreams tonight, perhaps Saturn will be there. Perhaps you will find yourself drifting above those rings, watching the particles stream past in their endless orbits, feeling the peace of that vast silence, that enormous patience, that ancient dance of gravity and motion. Perhaps you will see Titan through its haze, or watch Enceladus spray water into space, or observe the hexagon at Saturn's pole, maintaining its impossible shape. Perhaps you will simply float in the darkness, surrounded by stars, feeling small and yet connected, insignificant and yet part of the whole. Or perhaps you will simply sleep, deeply and peacefully, your mind at rest, your body relaxed, the day's concerns released into the darkness. And that, too, is exactly as it should be. Saturn will be there when you wake. The rings will still orbit. The moons will follow their paths. The universe will continue its slow unfolding, patient and vast and beautiful. There are more stories waiting if you need them, more worlds to visit in imagination, more mysteries to explore from the comfort of darkness and rest. The universe is generous with its wonders, endless in its capacity to inspire awe and curiosity and peace. Each planet has its character, each moon its story, each ring system its particular beauty. We have only begun to explore them, only started to understand the mechanisms that shape them, only touched the surface of the knowledge they offer. But for now, for this moment, Saturn is enough. Its rings are enough. The gentle facts about particles and orbits, about moons and gaps, about the slow, patient processes that create beauty on such an immense scale. These are enough to carry you into sleep, to ease the transition from waking to rest, to provide a soft landing place for consciousness as it releases its grip on the day. You are safe here, in this darkness, in this quiet. The universe turns according to laws that care nothing for human worry, that operate with perfect consistency regardless of our concerns. There is comfort in this impersonal vastness, this indifferent beauty. Saturn does not need your attention to continue existing. It does not require your understanding to maintain its rings. It simply is, and will continue to be, long after this night has passed, long after all the nights of your life have come and gone. Rest now if you can. Let Saturn's rings orbit in your imagination. Let its moons follow their paths through your dreams. Let the vast patience of that distant world remind you that time moves slowly for some things, that not everything rushes, that beauty can persist across ages. Let the facts and numbers fade into feeling. Let the details blur into wonder. Let the whole story of Saturn and its rings become simply a sense of peace, of connection, of being part of a universe that contains such marvels. The night is long enough for rest. The darkness is deep enough for peace. And somewhere out there, beyond the atmosphere, beyond the moon, beyond Mars and the asteroid belt, Saturn continues its ancient orbit, its rings catching the sunlight, its moons dancing their gravitational dance, patient and serene and beautiful, now and always, a constant presence in the vast dark sea of space, a reminder that the universe creates beauty not for any purpose, but simply because the laws of nature, operating across time, cannot help but do so. Sleep well, if sleep will come. Rest easy in the knowledge that the universe continues, that Saturn endures, that the rings will still be there tomorrow, and the next day, and for all the days to come. You are part of this universe, made of its materials, subject to its laws, connected to everything that exists by bonds of physics and chemistry and the shared history of matter itself. You are, in a very real sense, related to Saturn, to its rings, to its moons, to everything that orbits that distant sun. And with that thought, let consciousness fade. Let the day release you. Let sleep come in its own time, in its own way, gentle and natural as the orbit of ice particles around a giant planet, as inevitable as gravity, as peaceful as the vast silence of space. The story of Saturn will be here if you need it again. The facts will wait. The wonder will remain. For now, simply rest, simply be, simply let go into the darkness and the quiet and the peace.